Hello everyone, welcome to my channel Learning from Data. Today I'm going to talk about simple stats models summary explanation. Regression analysis is the bread and butter for many statisticians and data scientists. We perform simple and multiple linear regression for the purpose of prediction, and we always want to obtain a robust model which is free from any kind of bias. If there is any bias incorporated in the model, then the model is not robust at all. In this article, I'm going to talk about the summary output of Python's Statsmodels library using a simple example and explain a little bit how the values reflect the model performance. For the purpose of demonstration, I will use Kaggle's salary dataset, which is an open source dataset. The dataset has two columns, years of experience and salary. It is expected that the higher the number in the column, years of experience, the higher the value in the salary column. I have added two more columns, which are projects and people managing. So the projects column represent how many projects the employee is involved, and the people managing is the column which represents how many people that employee is managing. Let's quickly proceed to the notebook that I'm going to show you. This is the Jupyter Notebook that I will go through. First, import all the necessary libraries. We need pandas, numpy, we need statsmodels. Then I'm going to read the salary CSV file, which has 4 columns. Initially, there were only 2 columns, years of experience and salary. I have added 2 more columns, which are projects and people managing. The purpose is to introduce more numeric columns in the dataset and see how more variables can impact the model. Let's see how the salary varies against each of the independent variable. We have 3 independent variables here, so which are years of experience, projects, and people managing, and the only dependent variable here is the salary. The scatter plot of people managing shows a little bit linearity. The projects shows it's also linear, and the years of experience is also linear. As a matter of fact, it is more linear than the previous 2 variables. Then create the model. I am using the smf.ols command, which is ordinary list square. The formula is salary, the independent variable, and all the independent variables are here. And we put the data and we feed the model. Then here comes the summary. Let's run this one first. Okay, I didn't read this one. Okay, let's create the model. Okay, done. And then this is the model summary. I'm going to talk about each and every parameter. Those are shown here, and explain a bit about those parameters and how the values of those parameters represent the model's performance. Okay, let's move on. The first parameter is shown as the dependent variable, which is very obvious. We have only one dependent variable, that is salary, and we have 3 independent variables shown here: the years of experience, projects, and people managing. The next one is the model, which is OLS, that is ordinary list square. The purpose of this model is to reduce the sum of list squares. So that it can find out the best fit among all the linear fits. That's why it's called least square. It reduces or tries to minimize the sum of all residual squares. The next one is the method. This is least square. We have date and time. We have number of observations 30. So we have 30 rows in our dataset. df residuals, which is here 26, and df model is 3. So df is a degree of freedom. We have 3 independent variables. So we have the model df3, and the degree of freedom residuals is calculated as the number of observations minus this degree of freedom for model minus 1. So 30 minus 3 minus 1, which is 26. On the right side, we have r squared, which is often called the coefficient of determination. It actually explains how much of the variation in our dependent variable can be explained by the independent variables that we choose. In our case, we choose 3 independent variables, and the r squared value is quite high, which is 0.959. That means 95.9% of the variation in the salary can be explained when we incorporate projects, people managing, and years of experience. If we include less number of variable, the r squared will change. Let's say we want to include only, let's say only the projects. Let's run this one. When we include only the projects, the r squared value drops. It is now only 82.5%. Therefore, the more variables we include, the higher the r squared value. Run this one again. We got 95.9%. The next one is adjusted r square. The problem of adding more and more independent variables to the model is it will always increase the r squared value. That doesn't necessarily mean the model has become more and more robust. So we need to be very careful when we add more and more independent variables. When we add more variables, we have maybe there is some multi-collinearity. There may be some unnecessary variable that we're including, even though the variable has nothing to do with the dependent variable. It will increase the r squared value. So there may be some unnecessary inclusion of variables, so we need to be very careful about that one, and we need to always avoid multi-collinearity. That will make the model weaker. The solution of this issue is to always look for the adjusted r squared value, which basically punishes the addition of more and more independent variables into the model, and it just adjusts the r squared value over here. Before moving to F statistics and probability of F statistics, let's discuss the log likelihood and AIC and BIC first. The log likelihood value is a measure for fit of the model with the given data. It is useful when we compare 2 or more models. The higher the value of this log likelihood, the better the model fits the given data. It can range from negative infinity to positive infinity. Let's say we want to include all these 3 independent variables to predict the salary. Let's run this one, and we can see that the log likelihood value is -300. And let's say we want to compare it with another model. If we want to include only the projects here to predict salary, let's see how the value changes. Okay, the log likelihood value now is -322. In terms of log, the previous one, when we included all the three variables, we got the log likelihood value of -300. That value is actually higher. That means when we included all the three variables, the model becomes more robust. That means the model is more dependable. And when we included only one, the log likelihood value becomes -322. That means it dropped. Actually, if we look at the R squared value, it goes hand in hand with the log likelihood value. In this case, the R squared value also dropped here because we included only one variable. Okay, the next thing is AIC and BIC. One of the primary goals of the regression model is to explain the variation in the dependent data as much as we can by the independent variables. To do so, we want to increase the R squared value over here that I showed earlier. Adding more and more variables to the model will facilitate the process of increasing the value of R square. There are a few other metrics that we can also use to indicate the robustness of the model. For example, these two variables, AIC and BIC. AIC stands for Aic Information Criteria, developed by a Japanese statistician, Hirotugo Aic. And BIC stands for Bayesian Information Criteria, and we're going to see the equation for these two parameters now. So here is the formula for AIC as well as BIC. SSE stands for squared sum of error, N is the number of records, and K is the number of variables incorporated in the model. In essence, AIC and BIC penalize adding more variables in the model. When developing a model, the goal is to minimize the values of AIC as well as BIC, whereas if we use R square as the metric, the goal is to increase the value of R square. We missed one of the parameters over here, which is covariance type. Covariance type is typically non-robust, which means there is no elimination of data to calculate the covariance between features. Covariance shows how two variables move with respect to each other. If the value is greater than 0, both move in the same direction, and if the value is less than 0, the variables move in opposite direction. Covariance is different from correlation. Covariance doesn't provide the strength of the relationship between the variables. It only shows the direction of movement, whereas the correlation value is a normalized value and it ranges between -1 to +1, and correlation provides the strength of the relationship. For example, if the correlation is very close to +1, the correlation indicates that the if one of the value moves in higher direction, the others also move in the same direction, and this relationship is very strong. If we want to obtain robust covariance over here, we can declare the COV underscore type as HC0 or HC1 or HC2 or HC3. However, the stats model documentation is not that much rich to explain all these. HC stands for heteroscedasticity, consistent, and HC0 implements the simplest version among all. Let's say if we want to implement the instead of non-robust, we want to implement a robust type of covariance, we can declare over here covariance type, something like this. So this thing goes inside the model.fit, and we can have a robust kind of covariance. The coef column over here represents the coefficients for each independent variable along with the intercept value. Standard error is the standard deviation of the corresponding variable's coefficient across all the data points. The t column provides the t values corresponding to each independent variables. For example, here projects, people managing, and years experience all have different t values as well as different p values. Typically, when p value is less than 0.05, it indicates a strong evidence against the null hypothesis, which states that the corresponding independent variable has no effect on the dependent variable. T statistics are used to calculate these p values. A p-value of 0.312 for projects over here says us that there is 31.2% chance that project's variable has no effect on the dependent variable, which is salary. It seems that years of experience it has a p-value of 0.000, which is essentially 0. So it says us that the data for years of experience is statistically significant since it is less than the critical limit, which is 0.05. In this case, we can reject the null hypothesis and say that years of experience, this variable, is significantly controlling the salary. There are some other values over here, the column 0.025 and the column 0.975. These are the measurements of values of our coefficients which are lying within 95% of the data, or in other words, within 2 standard deviation. For example, the project's coefficient value is 304, and the column 0.025 shows here negative 301, and the column 0.975 shows value 909. This says that the initial 2.5% of the data are below this value, and the top 2.5% data are above this value. So the majority of the data, which is 95% of the data, lies between this limit. Let's move to F statistics and probability of F statistics over here. F test provides a way to check all the independent variables all together if any of these are related to the dependent variable. If probability of F statistics is greater than 0.05, there is no evidence of relationship between any of the independent variable with the output. If it is less than 0.05, we can say that there is at least one independent variable which is significantly related to the output. In our example, the p-value is less than 0.05, and therefore we can say that at least one variable from the independent data is related to the output variable, which is salary. We have seen previously that years of experience is significantly related with salary, but others are not. So here we can see when we did the individual t-tests, we see that projects, the p-value of projects is greater than 0.05, people managing, which is also greater than 0.05, but only years of experience is significantly related. So the probability of F statistics also tells us that at least one of the independent variables is very much related with the output variable, and which is also the case here when we look at the probability p-values here down here. However, there may be some cases when the probability of f statistics may be greater than 0.05, but one of the independent variable shows strong correlation. This is because each t-test is carried out with different set of data, whereas f-test checks the combined effect including all variables globally. Let's move to the parameters down here. Omnibus test checks the normality of the residuals once the model is deployed. If the value is 0, it means the residuals are perfectly normal. Here in our example, the probability of omnibus is 0.343, which indicates that there is a 34.3% chance that the residuals are normally distributed. For a model to be robust, besides checking the R-squared values and other rubrics, the residual distribution is also required to be normal, ideally. In other words, the residual should not follow any pattern when plotted against the fitted values. Skew values tell us the skewness of the residual distribution. Normally distributed variables have a skew value of 0. Kurtosis is a measure of light-tailed or heavy-tailed distribution compared to normal distribution. High kurtosis indicates the distribution is too narrow, and low kurtosis indicates the distribution is too flat. Kurtosis value between -2 and +2 is good to prove normality. To get an idea of this condition number, let's start with only one independent variable, which is projects over here. Let's run this one and we get the condition number 40.6. Next we include all the three variables and run this one again, and we get a condition number 56, which is higher. This means that there might be a little multicollinearity present in the given set of independent variables, which are projects, people managing, and years of experience. I have written a Medium article for this topic, which is a simple explanation of Statsmodels, a linear regression model summary, which explains all the parameters that we have discussed in this video. It has gone through a sample dataset. This is the same dataset that we went through in our video, and it has the explanations of all the parameters that we discussed. I will have this link in the description of this video, and readers can go through this one, and I have also linked to my GitHub page, and readers can go through the code and run in live. And if you have any feedback or any comment, let me know. That's all for today. See you in the next video.